Hello everyone, this is a video about Titanic dataset. This is one of the first Kaggle competitions. It's especially useful for beginners, and I'm going to break it down into simple steps, how to do it and how to become a data scientist or machine learning expert. Right, so let's begin. I've got this notebook of the whole solution. The first thing you want to do is to automate the loading of the dataset. So yeah, I'm importing all those libraries I need. I'm doing matplotlib inline, special function. It basically makes all the plots prettier and better. And then I'm doing the automated download. So the dataset is called Titanic, and you actually need to use the Kaggle API to download it automatically, right? To use Kaggle API, you need to get the API key and install it. You can check the tutorial about how to do it, like in other videos, but I'm not going to cover it today. So I authenticate the Kaggle, set the dataset path, basically. So that's the Titanic project. Here is the Explore Titanic. It's the main file actually. There is the datasets folder where we're gonna extract the dataset, which is originally in zip file. And here are some figures I saved. Okay. So how do we load the dataset? First, we need to, we load it to the path of the dataset. And now in the dataset path, so in this dataset folder, we've got the, let me show you. So if I delete all of those, now, if I delete all of those, okay, I've deleted all of those files in the dataset folder. I'm going to show you how it loads. So first, when I run, you can see the Titanic zip file right here. It contains all the 3 CSV files of the Titanic data. So then we need to unzip and unpack the file. To do that, we need to use the library zip file. We tell it what's the path of the zip file, and then extract all using this line. So yeah, we're using the object zip file from the library zip file to extract all the data. And then we remove the zip file, and there's just data left. So if I run this kernel, you can see it. Yeah. So first, all those 3 files were unzipped. And then os.remove removed the Titanic.zip file. Great. We now have automatic data retrieval. Here's an auxiliary function to save different plots, different figures in the future. So here you can take a look. The main thing is plt.savefig. plt.savefig just saves the current figure in the matplotlib, kernel. Yeah. So then I actually read the Titanic dataset in a pandas data frame. So I specified the categorical attributes and create a mask to filter out categorical attributes from the numerical. Right. But then this thing got deprecated and I didn't use it actually. So really all the categorical attributes are those 5. And the only numerical one is age. Okay, so you can see how age looks like. We've got 891 entity, 891 rows in our train data, and it's filled with values. So let's just see what values do we have. What is our data really? So using the head method, when we look at the top 5 rows, we can see that there are 12 different features which we're going to use to determine whether a person survived or not. As you can see right now in the train data set, we still have got the survived class, the survived feature, but it is actually our target feature, so we're going to remove it whatsoever in the end. We've got name, sex, age. It's all self-explanatory. So what is P class really? P class is the class of the fare. So first class would be like the top class, the most expensive one. And the second is less expensive, and the third one is just the standard one, the econom. Yeah. So what is SIB-SP? SIB-SP means siblings or spouse. So how many siblings or spouses are there of that person? We can see that Mr. Owen Harris had 1 sibling or spouse, and Pa-ch means parents or children. So how many parents or children did he have on the ship? He had 0. Ticket is the name of the ticket. Fare is the cost of the ticket. Cabin is actually the location of the passenger. And embarked means from which ports did that specific person embark, really. Okay, so we've seen the data. What can we use here? Now, to test the hypothesis that the people from the first class survived more than the people from the second or the third class. Also, we could use age to split people into age groups. Sex, I think it's quite important. So male, female, fair, and cabin, really, because it tells you the location of people. And location is really important. Just visualize those initial features with histograms. Passenger ID is quite useless because it's just the same as index plus 1. It's of no use. Survived. We can see that around 330 people survived and 560 did not. Right. So that's our ratio of survival. There were the most people of the third class, around 490, and less of the second and first. Most of the people didn't have any parents or children on board, as well as siblings or spouses. And as you can see, most of the people's age was from 18 to around 40. And yeah, the majority of people had a low fare. Okay, so that's just some info about our data. As you can see, the column age actually has not all the values. So there are missing values. around 180 missing values, which we need to fill in for the algorithm to work properly. Then we also have cabin, which misses like 700 values. That's massive. So we really have to look into that and try to work around the cabin thing. And embarked, we're just missing 2 values, really, just 2. Okay, so there are 3 columns where we need to fill in some data. Okay. There's also the description of all the features. Yeah, it's basically, it's similar to .info, really. Yeah, you can see that the mean age was 29. Yeah, that's the only useful information I can see right now. Okay. This graph is really useless. Yeah, it doesn't do much. Let's move on to other things. So first, we need to create transformer classes, which help us to build a pipeline of data pre-processing. So basically, what we want to do is anytime we load the data set, we just apply one function, one pipeline to that data set, and all the different changes to the data happen immediately during that single pipeline. And we need to build different parts of that pipeline. If you don't know what a data pipeline is, basically a data pipeline is the whole process of data being inputted and outputted into something different. So it's sort of black box which transforms your data into something new. It can extract features, do feature engineering, create new features, and all sorts of stuff just with data. It's about data processing, right? You can imagine pipeline as like a conveyor belt where data is like a package which gets transformed and refurbished on every like station, and then at the end what is outputted is like a big gift, a nice box. Okay, so we start from editing cabins. What we want to do with cabins is to, let me show you. You can see that the cabins that are not missing, they have some letter and some numbers. Basically, the most important thing out of this is the letter, because it indicates the section in which a passenger lived. It doesn't really matter whether they lived in like room 85 or room 123. If they lived in the same section C, it doesn't make much difference. So let's look at more values actually. Oh. Okay, I need to restart. Because the data was changed. Yeah. The data was changed, sorry. Okay, yeah. You can see that, for example, person number 10, Miss Margaret Root, age 4, so just an infant. She lived in cabin G6. So we would only want the letter G for that person. Okay. So how do we do that? We use a custom transformer. What a transformer is an object which fits on your data. So it's fitted to your data and then transforms it based on some principles. Every transformer must have two two special methods. It's first fit, and second transform. Basically, fit is what we get from the data, some special values. In this method, we don't get anything. And transform is how we transform the data. In the case of editing cabins, to only take the first letter, what we do is we apply this lambda function, which inputs an element and gives out the first letter of that element. An element would be just each cabin. And we apply it to each cabin, right? And then return the clean data set. We also preserve this clean data for later because we'll use it. Fill empty is a transformer which fills all the empty values. This is age, cabin, and fare. Yes. Placeholder transformer just does nothing, really. Okay. So here is the pipeline which cleans the data and prepares it. So it fills all the missing values. That is called cleaning. And then edits cabins so that only the first value is accepted. Here is our first pipeline. Okay. So let's actually see how does Titanic look after applying this pipeline. So what we do is we say that pipeline clean dot fit trans. Alright, so I fixed an issue with some lags. Let's return to the dataset and cleaning. As you can see, when we fit transform Titanic using the pipeline clean we've just created, our cabins turn into single letters. For the missing values, I chose letter O, just as an arbitrary letter, to fill in them. Also, you can see that fare has changed. Did I miss that point? Yes, actually, in fill empty, we're also changing the fare. We're basically splitting it into 3 categories: low, medium, and high. And the way we split it is in a way that every category has the same number of people. So, for example, if we have 900 people, then in low there will be the lowest 300, then the medium 300, and the highest 300. Yeah, for that we use pd.qcode. Alright, great. So we've filled missing values, we've changed a bit of our data. This is a weird graph. It used to mean something, but it doesn't now. So then I've created my binarizer, which is literally a label binarizer, but it just didn't work, so I had to create my own transformer for that. We use it to encode sex. So basically, male or female would be 1 and 0 correspondingly. So here I think male is 1 and female is 0. Then for transforming the categorical values, we use something called one-hot encoder. It's a cool thing. Basically, what is one-hot encoder? Imagine B class. Yep. We have 3 different values, 1, 2, and 3, right? And we actually want the model to recognize each of those. So basically, we split this class into 3 additional columns for each different unique value. And it is basically, for each row, it would be a 3-dimensional vector with those 3 columns where only one column would be 1 and others are 0. So for example, if the class 3 is encoded as 100, so let's say that 3 is 100, 2 is 0, 1, 0, and 1 is 0, 0, 1. This is how our classes might be encoded. Yeah. So basically we would add 3 additional columns. For the first row, where p class is 3, it would be 1, 0, 0. The first column value would be 1. The value of the second column be 0, and the value of the third column will also be 0. And similarly for others. Why we do it, you might ask. Basically, models don't recognize very well such concepts as class 1, class 2, class 3. It is easier to recognize that one of them is true and others are false to work better. Yep. That's it. Yep. So in the main pipeline, we apply binarizer to the binary features, which is only sex, male or female. Then apply one-hot encoder to categorical values. These are P class, fair, embarked, and cabin. I think there are 9 different cabins. So A, B, C, D, G, and so on. Only 3 different values of embarked. 3 categories of fair, low, medium, high, and 3 classes. Okay. And the only numerical feature is is age. The only numerical feature is age. Right, and others are all but those. So we use binarizer for binary data, one-hot encoder for categorical, and standard scaler for numerical. Why we use standard scaler for numerical data? The thing is, when we have age as 30, 60, 50, 10, it doesn't bode well with it's not suitable for all the machine learning models. Any model you take, you don't want to input values out of the range like -2 to 2. Usually it's best to keep all the values from -1 to 1. That's what we're doing with standard scaler. Okay, remainder equals pass-through means that all the other unspecified columns will be left unchanged. Right, so then we actually don't use those 3 columns, name, tickets, and passenger ID, so we want to drop it. And drop it functionally, not just with code, so that it can be reproduced, this whole operation. So we use this function called dropper, which I created. Basically inputs a PD data frame and drops all the columns. Then we wrap this dropper function into a function transformer so that it works in a pipeline, so that it's suitable for the pipeline. So we pass it the dropper function and the keyword arguments. So these are all the arguments with some keyword. Here we have calls, which is this argument, and we pass in the categorical columns, which are those, so that they are dropped. And the second function transformer we are making is the binarized relatives. So basically what it does, it takes those siblings and spouses and parents' children, and each of them, you can actually see that it can be more than one. So you can have more than one parents or children. So you can have like 3 children and the part would be equal to 3. This doesn't really matter, I think. I think the most important thing is that you either have those relatives or you don't. So all the values that are greater than 1 will be just converted to 1, and zeros will be left. So it will be 0, 0, 0, 1 here instead of 2. Here 1, 1, 0, 1. So that we're only left with zeros and ones. 0 means that there are no siblings or relatives, and 1 means there are, basically. So you really want to simplify your data, because all those machine learning models are not that smart if you feed it with rubbish data. That's a very crucial principle of machine learning. And here we are creating the full pipeline. First, we're dropping unnecessary columns. Then we're binarizing the relatives. Then cleaning the data and using our main pipeline as a part of the main pipeline, of the full pipeline. So in the full pipeline, we actually use 2 different pipelines, pipeline clean and pipeline main. So there's a sub pipelines. And this is the structure of our full pipeline. Yeah. Jupyter Notebook is really good at visualizing data structures. As you can see all the steps, all the parameters, standard scalar, pass-through, one-hot encoder, all the things really. Those function transformers. Okay. At this step, we're transforming, well, first we are fitting our Titanic to the full pipeline so that it understands the context. And then we're transforming the Titanic dataset. Let's actually run all the code. Okay, while it runs, this is an auxiliary function, collapse, which I'm going to use to basically get all the full columns that are left. The thing is, what happened? Oh yeah, we cleaned the data, which disrupted the whole pipeline. Okay, so it's functioned okay. Okay. Yeah, now it's right. So the thing is, when we transformed the Titanic dataset, let me show you the actual transformed structure we got. It is a NumPy array. It doesn't have columns. Yeah. And what's the shape of this? Let's actually select the 0 to 5 rows and all the columns. 0, okay, just 1. So this is 1 vector, 1 row, 1 final row, and has like 20 something columns, 20 something different features each row. And what are the names of those columns? So that's the thing we basically lost. We need to resurrect it. Let's return it. And for that, I need the function collapse. It doesn't really matter what it does, but it helps me to retrieve those columns. So in the final file, the transformed dataset, the columns are sex, 3 p-class values after the one hot encoding, 3 fair values columns, 4 embarked, because I actually just realized that I didn't impute those 2 missing values for embarked, and it counts the missing value as a different category. So it creates a fourth category for embarked. For a missing value, we have 9 cabin, different columns, age, survived, sibling spouses, and parents chosen. Then we actually rebuild our data frame using the columns so that it's pretty and nice. And we can see that everything works. Here you can see that's our final transformed data frame of Titanic, with all the categorical features neatly outlined as one hot vectors and age scaled. Then we want to see the correlation. The correlation of our data. Yeah, and I actually filtered all the features which correlated less than 0.3 out. Because it's better to make a more simple, it's always better to simplify where possible your input data. So if correlation is less than 0.3, it's just not helpful. Just gonna make some noise. Let me show you the correlated columns that are left. Oh yeah, I didn't run it. Just a second. Yeah. So actually, the only columns which are left after filtering all the columns where correlation is less than 0.3 is B class 2, cabin 7, and survived. Oh, and sex. Yes. Survived is actually going to be get rid of, because the correlation of survived with survived is 1, and it's no help. We're going to drop this column. It's our target label values. Yeah. So the Titanic with just the data set with just those features is going to look like that. Very simplified. Yeah. We're posting the histogram of survived versus sex. Yeah. Here is a heat map of 2 random features and their binary value. It's actually not representative at all. It's just a mess. Yeah. I'm not yet there. Yes, I'm not yet an expert. So, yeah. So I produce sort of those graphs, but I will get better. I'll definitely get better. Okay. So, these are those. Okay. So now let's go to the model part, the coolest bit where our model actually learns. First, we need to split the training data set into 2 bits. The Titanic train and Titanic validation. Actually, in all the machine learning projects. So this is the coolest bit, actually, right here. So I'm going to tell you about why do you need to split your training data set into 3 different sets. These 3 sets are the training set, validation set, and test set. Initially, when you have a data set, what you want to do is just get rid of the test set immediately, straight away. Just get rid of it. Put it away. You don't want to look at it until the end. This set is going to be used to determine the actual quality of your model, the accuracy, unbiased accuracy, which is going to resemble the real world scenarios the most. So you don't want to do any fine tuning on the test set. You're just going to test your model and see what level of performance it gets. Right. the validation set and training set, what you do with them. When you're selecting the model, there are actually many different models you can take. What you want to get to is train the model on the train set and then test it on the validation set. Measure its score on the validation set. And you see which models works best, which models is the most accurate. The thing is, if you didn't split the whole data set into 3 sets, but only 2, let's say you only split it in the train set and test set. When you're choosing your model and then tuning the hyperparameters of the model based on the accuracy on the test set, you're actually just fine-tuning to that particular test set. And if it performs well on that test set, it doesn't necessarily mean that it's going to perform well in the real-world scenarios with new data. So it doesn't mean that it generalizes well. Maybe it just overfits the test set. Actually, it's quite likely if you do that. So you use validation set to tune the hyperparameters and select the best model, and then test it on the test set to measure its actual performance. So that's why we're splitting the train data into Titanic train and the Titanic val of the data. And actually, the test set is already split even before I did that for us, so that we don't make this mistake by the Kaggle. Yeah, so basically all the Titanic things I did were on the train set before that. And the test set is just a very different thing. I didn't even read it, didn't even open it, and I shouldn't. Yep. Okay. So I was splitting it and leaving 0.2. So the ratio of the validation set to train set would be 0.2. So 20% of the whole Titanic filtered train data would be for validation set. Then I'm also using the random state to get consistent results. Yep. So here we're splitting the Titanic train set into Titanic train, the actual train, and Titanic val validation, with 20% of the whole set being validation and the rest is Titanic train. So the labels would be the survived column, as I mentioned before, and we need to convert it to list so that model can input it, because it doesn't recognize the pandas series, which is returned when we do that. So we need to convert it to NumPy list. And the features will be Titanic train drop survived. So all the rest from survived dot copy. Also, I'm preparing this variable called indices, where I put the basically the indices of the columns we selected from the original Titanic dataset. Let me show you. Yeah, didn't run it again. Let's run it. So these are 0, 3, and 18. So in the original Titanic dataset, or actually in the prepared Titanic dataset, not split one, not before I selected on the features with correlations of more than 0.3 in that prepared dataset, the corresponding indices are 0, 3, and 18. These are sex, class, I think it's class 2. Let me check it. It's sex, P class 2, and cabin 7. These are those. I'll use it afterwards for the test set. I'll show you then why do I need those indices. Alright. So And yeah, and we're also doing the same for validation, labels, and prepared. Cool. Let's look into different models. First, we have many binary features here. Yes, it's just zeros and ones, almost all the data. So a good model here, really, the first thing that comes to mind is to use a decision tree or some tree-based model. So let's start from the decision tree. We fit the decision tree on the features with those labels. We specify the number of nodes to be 100. And then we see what accuracy we get on the train data. It's the same, 80%. So it trained on those train data for the labels. Then if you feed this training data again to it, and if you fit this training data again and get the predicted values and calculate the accuracy, it's actually not going to be 100%, because the model tries to not overfit, so it doesn't learn all the stuff. So that's a good thing, because it's often just giving you 100% accuracy, which you don't want to see when you're checking the trained set, which it was trained on. The actual accuracy performance is better represented by validation set. So yeah, well, with the trained model, we predict from the features what will be our labels, and then compare it, and we get 73% accuracy. This is going to be something similar to the actual accuracy on the final submission on the test set. Okay, so you can't see it, but I've tested 7 different models: random forest, ADA boost, gradient boosting, SVMs, some reach classifiers, passive aggressive classifiers. Don't really need to know what is that, but I just try to test different models. So testing different models turned out that the random forest classifier, which is based on decision tree, it is a tree-based ensemble model, works the best. So this is the model we're going to use for Titanic. We fit it. We can see it. Then we retrieve the importances of our three features, how much they determine the actual label. We can see that sex has importance 0.7, whereas B class 2 is 0.15 and cabin 7 is 0.1. You can see that the stark difference of how much sex really matters. So being a male or female really changed the survivability rate for people on Titanic for some reason. All right. So then let's calculate the accuracy of the random forest, the accuracy on the train set, the accuracy on the validation set. And then finally, let's go to the test set. We're almost done. So let's fetch the test set. It's going to go through the full pipeline. This is why we actually did this pipeline, so that we can just call one function and the whole dataset is going to be transformed. Here, let me show you actually the Titanic test prepared. You can see that it's a NumPy array. This is where we're going to use the indices of our actually selected features. Yeah, so in the next line we're doing just that. So we're only left with sex, P cluster, and cabin 7 features. And these are all final predictions, which we're going to zip into final submission. CSV file. So we just zip it with range from 892 to 1310, because these are our passenger IDs from 892 to 1309. So here's our file. And then we turn it to a CSV file and save it as submission1.csv. As you can see, that's our submission. And then we post it on the Kaggle website. And that's it. We're done. So now, yeah. So basically, that was the whole machine learning project. I didn't say it's going to be very difficult, but if it's the first time you've seen a machine learning project, but you want to be a machine learning specialist, like expert, you want to excel at this, or you just want to, explore machine learning, right? That could be difficult for you because you didn't know maybe even Python programming. Yeah. However, I really hope you did find it useful, this guide. Now let's actually see what's the final accuracy we get. Yeah, so you can see here are my submissions. The first submission was actually accuracy 55%. Why, you might ask? The thing is, during that submission, something got wrong in the pipeline, something with those indices, and it just gave me basically random values. So it was a bit skewed. But the final submission is 77.5%, which is not too bad. It's fine. So given all the data we had, determining whether a person survives with 77.5% accuracy is actually quite good, I think. Okay, so let's summarize what we did in this project. So we did some data preparation, pre-processing, cleaning, filling those missing values, then selecting and extracting different features, a bit of visualizing. Then we selected the best model, trained it, tested the accuracy. There were some tweaks to the data pre-processing when I understood that the accuracy is not satisfying. Yeah, and that's it. In this project, there is a lot of room for improvement, and I know that. Yeah, it's not my best work, but I'm going to improve. And in the next episodes of just going through different data sets, I will show you various techniques of how to crack those machine learning projects and become better. So if you are new to machine learning and you really like it, please subscribe and like, and see you in the next video.